Hey guys, this is Sauce123 for RunItOnce.com, and today we will be doing Toy Gaming Episode 3. So, to start things off, I'm going to move this video a little bit faster than the previous Toy Gaming episodes. I figure you guys can slow it down or re-listen to stuff if you don't get something, and I would prefer to move quickly. So, here we go. I have chosen to look at some of these Ace, King, Queen games from Mathematics of Poker, and I think they predate Mathematics of Poker. I guess they're Mike Caro games from like the 60s or something. They're fairly simple, but I think they're illustrative, and let me explain why they're illustrative. So Nick Howard, one of our new Run It Once coaches, made this post in the High Stakes No Limit Hold'em thread, challenging a fundamental principle of game theory. The fundamental principle is this, that in game theory, you're not supposed to make plays that have a negative expectation in poker, because you can just fold or check and fold, and the expectation of that play is 0. The idea seems to be, according to Nick, that there might be spots where if you make some bluffs that are negative EV, you add enough extra value to your value bets to increase the value of your strategy. And because you have to make negative EV bets, in order to get that extra value, it's worth it to make some negative EV bets once in a while. And I'm going to look at a couple of toy games today, 3 to be exact, that I think shed some light onto this seeming contradiction, or question, I guess. So, scrolling down through this post, you guys have probably seen it before. Cliffs, this is Nick's point. If we assume that a particular hand is negative EV in line 1 relative to line 2, does that automatically mean that line 1 is a suboptimal strategy? My answer is yes. That's what it does mean. Is it possible that hands can perform ritual sacrifice to serve the EV of the range on the whole? That's a fun way of putting the point that should you make a bad play with a hand in order to increase the EV of your range? And I think the answer to that is also no. So, let me bring up the slides. So here we go, Toy Gaming Episode 3. This is going to be Ace, King, Queen games. So, our first Ace, King, this is how the Ace, King, Queen games work. There's 3 hands in everyone's distribution. The hands are either an ace, a king, or a queen. And there is card removal. So, for example, if in position holds a queen, then out of position only holds an ace or a king because the queen's out of the deck. And just some facts about these distributions that are common to most of the toy games we looked at so far. The distributions are symmetric, meaning that each player has exactly the same distribution of hands. There are no draws, so if you have a king, you can't hit another king later. And out of position has to check and then call or fold, and that just simplifies the game tree quite a bit and allows us to zero in on, solving the half street game. And we're going to look at limit betting of various sizes in this game and no limit betting. No limit betting in this case means that we can bet whatever we want with any of the hands in our range. So, this is going to be the first species of Ace, King, Queen game. This is a limit betting Ace, King, Queen game, and the betting is either half pot or checking. Obviously, we can check behind as in position. Okay, so generally when you're doing these games, it can seem intimidating because it's like, oh, I have to do math. But you don't really have to do math. Most of the solving of these games you can basically do in your head just by thinking about things logically. So I'm going to take you through that, and you have these, exciting slides to explain what I was thinking. So one of the first sort of things you want to do when attempting to solve a game is you want to remove strategic options that are going to be bad for either player. That'll help you zero in on the plays that are more difficult to figure out, and which might involve a little bit of math to figure out the precise mixes of. So, starting with in-position strategy, he has an ace, a king, or a queen, and he has to figure out what to do with them. And he can either bet half pot with any of the hands, or he can check with any of the hands. So, there's a few strategies. So let's sort by hands. So if he has ace-ace, he's obviously betting because it's the nuts. If he checks, he wins the pot, and if he bets and our opponent folds, he wins the pot, and if he bets and our opponent calls, he wins more than the pot. So that's quite trivial. He should check king-king. That's because it can never gain anything. The reason for that is supposing that in position holds king-king, that means that out of position's range is going to be either aces or queens. If in position bets kings and out of position folds queens, that doesn't do anything for him because he's already beating queens. And if he gets called by aces, he just puts in a bet against the nuts. So it can't possibly be correct to bet king-king unless out of position was somehow going to fold ace-ace, which he's not going to do because it's the nuts. Okay. And then there's queen-queen, which is, of course, the trickiest hand in position's distribution. And the question is, should we bet queen-queen? If we should, how often should we bet? And how do we figure out how often to bet? That's going to be the real kicker. And we'll get to that in a little bit. And out of position, given we've already discussed in position, it's pretty obvious. He's going to be calling with aces. He's going to be folding queens, given that he has queens in position either has aces or kings. So calling with queens is obviously not going to be right for the chop because there are no chops. Aces is going to call because it's the nuts. And kings might call if in position is betting enough queens. Okay. Sounds good. All right. So now we're going to sort of reason out, how often to bet queens and how often out of position should call kings. So remember that we're at equilibrium if nobody can increase their expectation unilaterally. So, the unilaterally modifier here just means that certainly someone could increase their expectation if I said, oh yeah, so you don't bet aces anymore, and then I'll just call my kings. Now that would definitely increase my expectation, but I wouldn't be doing it alone. I'd need to rely on some mistake or some change in my opponent's strategy. So we're at equilibrium if neither player can increase their expectation against what their opponent is playing right now. Think about that for a little bit. That's pretty much how you do game theory, in my opinion at least the level of game theory that I do, which is, fairly novice. I just look to see if people can increase their EV, and if they can, I make them do it, and then I figure out how the other guy should counter. And if they can't, then I know I'm done. Cool. Now, if in position never bets queen, so I didn't properly qualify this next point. What is our sort of starting case? Well, let's just take the strategy for in position that I outlined before in the previous slide, which is betting aces, and we don't know what to do with queens. Let's just assume we check them for now. And let's see how in position responds, and let's see how much EV that gives us out of the game. Remember, what we're interested in is maximizing our expectation for both players. We're not so much interested in how often we bet certain amounts of certain hands. We're only interested in how that affects our expectation. Okay, so let's suppose we never bet queen-queen as in position. Then out of position we'll always fold king-king because when we bet we have aces. So we can now solve for the EV for in position's entire strategy. It's going to be 1 with ace-ace because we never get called. And then the entire game value is going to be a third of the time we have ace-ace, we win the whole pot. A third of the time we have king-king, and we win half the pot. And a third of the time we have queen-queen, and we lose the entire pot because we never beat the other guy's aces or kings. So that just sums to half pot, meaning that our positional advantage was worth nothing to us. Supposing we never bet with our queens. Okay, so can we do better? Well, yeah, we can. And the way that we do better is we bet queen-queen to start off with. The reason is because we're risking half pot to win full pot. And supposing that we bet queen-queen and out of position is folding everything but aces, that means he'll fold half the time. Because given that we have queen-queen, he has aces half the time and kings half the time. So the EV of betting with queen-queen is positive. It's greater than 0. So we lose half the pot half the time for negative 0.25, and we win the full pot half the time. So every time we're betting our queens, given that out of position always folds, we win a quarter of the pot, and that's certainly bigger than 0, which is our EV if we check. Okay, so if you're following along so far, you can call this sort of like iteration one. This is like, so we have a strategy pair, and we figured out that in-position can exploit out-of-position strategy of never calling with kings by betting all of his queens. And that gives us somewhere to go. So of course what we do is we figure out what out-of-position can do to combat betting all of his queens. And the answer is that he can call with all of his kings. And now in that case, out-of-position is never going to be folding because he either has aces or kings and he should call all of his kings. And now the EV of betting queen queen is going to be negative half the pot because it never works. So we've seen the two different strategies with king king that out of position can take, either always calling or always folding. And we've seen that the expectation for in position for betting queens ranges from positive quarter pot to negative half pot, depending on how often out of position calls with kings. And this shows that some mixed strategy is in order for both players. So there's going to be some frequency of queens that bet and some frequency of kings that call. Okay. So the question is, how do we solve for those frequencies? And the answer is, out of position is going to call enough king king that the EV of betting queen queen is 0, making it equal to checking. Remember, in that case, then in position will not be able to unilaterally increase the EV of his strategy because he can either bet queen queen or he can check queen queen 100% or 0% or however many percent he wants, but it won't do anything to increase the EV of his strategy, supposing that the EV of betting queen queen is 0. And the other side of the equilibrium is that in position is going to bet enough queens that king king has an EV of 0 to call, meaning that out of position can either call with all of his kings or none of his kings, and it won't give him any additional EV. Okay, so how to get there? We need to remember about card removal. So given that in position has queen queen, because when he has queen queen, he's just going to have. Oh, by the way, because we're using card runner's EV to check these numbers, we have to use two card combinations. So queen queen is the same as queen. It's the same thing. It's going to be a unique whole card combo without any removal effects. So given in position has queen queen, that changes out of position's distribution dramatically. He's going to have half aces and half kings. So to make the EV of betting half pot 0, out of position has to call with 2/3 of his range. So to start with, he's going to call with the nuts. So in this case, 50% of out of position's cards are just aces. So he's going to start by calling those, or 3/6 of his range. And to get up to 2/3 or 4/6, he has to call an additional 1/6 of his total hands, or 1/3 of his king-king combinations. And similarly, in order to make it, I don't think I actually wrote this here, but in order to make it so that king-king doesn't have a positive EV, in position will bluff with alpha of his queen-queen combinations, which in this case is going to be 1/3 of them, or he will be bluffing 1/3 as often as he's value betting, because he's betting half pot. Okay. So I'm just going to go over to this card runner's EV file. And here we have the half pot version of this game, just so you guys can see that. And you can see I did a little bit of fancy things here with card runner's EV to make these numbers come out. So they started with aces to queens, and I just deleted all of the hearts and spades combinations so that they have a unique combo of each hand. I think there's a slight bug here, so the numbers don't come out exactly right. I'm not sure how the bug works, actually. But it's close enough that it's not going to matter. So I'll just do an EV run here. I already solved this for you guys because we already, reasoned it out in the slides, and then we're just going to see if we're right by looking at the results. So here you can see that in position's betting half pot with his aces and 1/3 of his queens, and out of position is calling with all of his aces and 1/3 of his kings. So here we go. Aces has an EV of bigger than the pot now, because it's getting called by worse sometimes. And queen, queen, this should be an EV of 0. This is the bug that I'm talking about. I'm not sure exactly why that's there. I guess it's because of the fractions not rounding correctly. But anyway. And then for out of position, he's calling with aces for half the time, and he's calling with a third of his king combinations to make it so that he's calling 2/3 of the time that in position has queens. And you can see that the game value here for in position has increased from 0.5 to 0.53. And that's what playing the optimal strategy was. And what we can do here is we can use the maximally exploitative play for the big blind. And what that will just do is we'll say, okay, big blind, you can unilaterally do whatever you want with your strategy. What is the highest your EV can get to? And there it is. Oh, you actually can't run this when you do the deleted things. But in any case, because the EV of these kings is 0, supposing that, it's 0, supposing whether he calls or folds them won't do anything to his EV. So you can see that this is, in fact, at equilibrium. And you can see that by creating an optimal betting strategy, in position was able to increase the value of the game from 0.5 to 0.53 versus the initial betting strategy that we looked at. Okay, so this is sort of the interesting part of this game, is kind of the card removal effects. And we're going to start to get back to Nick's post soon, but not quite yet. So the twist is that when in position has aces, out of position is only going to call with 1/6 of his total range. The idea being that he's going to call with a third of his kings, and he's going to call with none of his queens, so that's 3/6 right there, and then another 2/6 for the 2/3 of his kings that he folds. I mean, he's only calling 6 at a time. Is that weird? Maybe it is, maybe it isn't. But actually, it really isn't. So if out of position called with 2/3 of his range, and I put, big air quotes here, to make in position indifferent from bluffing. But of course, in position is already indifferent, even though out of position is only calling with 1/6 of his range. But leave that aside for now. Then he'd be calling with all of his king-king and 1/3 of his queen-queen combos. And that's just nutty. I mean, obviously, if he was doing that, in position could exploit him by just betting aces. And nothing else would have positive EV. So I think it's important to see that some of these results that you see from game theory, like, or that get thrown around in the forums as game theory optimal, like, on the river, you have to call with 1 minus alpha% of your range, or else you'll be exploitable. Well, no, that's just not right. You have to call with enough of your range so that the other guy can't unilaterally increase their strategy. If there's strong card removal effects, you might only have to call with 1/6 of your range. You might have to call never. We're actually going to look at that case in a little bit as well. So you can't just use these sort of you can't think of these results from other toy games as theorems that will apply to any other toy game that we run into. Anytime you see a new toy game, you have to sort of reason it out and think about what's going to be correct in that situation and how the distributions are going to interact. And that's very important. And again, remember, we're at equilibrium when neither player can unilaterally increase the EV, the expectation of their strat. And in this case, they can't. And you can check that with the Card Runners EV file. If you like, I will post those files with the video so that you guys can play around with them at your convenience. And the way this result is typically phrased, in the way they do it in Mathematics of Poker, is that the bluff-catching player calls with 1 minus alpha hands that can beat a bluff. So in this case, it's 1 minus alpha hands that can beat queen-queen. That's worth thinking about for a minute, I think. So, given that we have queen-queen, they have to call enough to make us indifferent. And the card removal effects are taken into account in the solution of the game. And again, note that the game value here for in position is greater than our base strat of only betting aces. When we only bet aces, out of position would just always fold. That's how we maximize his expectation. And the expected value of the game was 0.5, and now it's 0.53. Okay, so that's the limit case with a bet size of half pot. Next, we're going to look at the no limit version of this game. And, okay, so the no limit version, we give imposition the opportunity to bet any size he wants with any part of his range. So how much should he bet? Well, it's going to be one sizing with ace-ace and some queen-queen, but how big? And I think that should be clear by now. The reason why it's one sizing is that all of our value hands have the exact same, I guess, status. They have the exact same removal effects, and they do the exact same against the other guy's range. So we're only going to have one bet size because we only have one value hand. And we know that to get paid off on our value hands, we'll have to bet some of our bluffs. And so we're going to bet that size with our bluffs as well. It certainly wouldn't be good to just bet a different size with our bluffs, or else we would just get called and lose that money. So one way to do this is just the brute force method. We know what the structure of the game looks like from the solution to the limit version. Out of position calls with 1 minus alpha of his king-king and ace-ace region for any bet size, i.e. king-king and ace-ace are the hands that can beat a bluff. And imposition bluffs alpha of his queen-queen combinations. And we just pick the bet size that maximizes the game value for imposition. So, we'd have a graph with both of these two strategies at equilibrium that we've expressed this way. And, maybe one imposition would bet a 10th pot, then, a 20th pot, and then he'd bet 30% pot, and 40% pot, and 50% pot, et cetera, et cetera. And then we would just see what the game value was for every point on that graph, and we can just pick the apex of the graph. And that's exactly what they do on page 152 of Mathematics of Poker, if you want to use that as a reference. And then there's also a derivation of that result in the same section, Mathematics of Poker, which requires a little bit of calculus. But I think it's explainable without any calculus, and certainly my math skills are not very good. So I believe I understand what's going on here, and someone correct me if I'm wrong. In this case, the result ends up being that imposition bets approximately 41% of the pot. And exactly that's the square root of 2 minus 1. So it's like 0.414 with a bunch of other decimal places of the pot. And the full derivation of this is on page 152. But the idea is that betting, they call this value 0.41% of the pot R because it's a value that gets repeated throughout Mathematics of Poker and various toy games. So they call this the golden mean of poker. I haven't found R as useful, but it's confusing because Lefort in his videos uses R to mean the amount of equity that we realize, or an estimate of the amount of equity that we realize in a given line. So people typically say that R has to be equal 80% for me to make this pre-flop call. And Lefort calls that, realized equity percentage. And then the Mathematics Poker guys use it differently to be this 0.414 number. So that's kind of confusing too. So I tend not to use R. Or if I do, it's with, someone who is very familiar with Mathematics of Poker in order to avoid confusion. But the idea is that betting R maximizes the size, as in how much we put on, times the frequency that out of position calls with king-king, which is where in position creates value in the game tree. So, for example, say we bet, we're going to actually look at this case in a little bit, but say we bet 10 times the pot. If we did that, then out of position would only call with aces, in which case we never get called by worse. So we'd actually make less money than if we bet significantly smaller so that we get called by king-king more often. Similarly, if we bet 0.001% of the pot, we'd get called by pretty much out of position's entire range. But we'd be putting so little money in that it wouldn't add up to enough to maximize the game value. So by betting 0.414, we maximize the frequency times the amount of money that the other guy puts in with king-king. So basically the idea is just we want to make him put in the most money with king-king that we possibly can. And that's how we do so. Right. The other thing about R, it's the ratio between the size of value regions in various betting games, among other things. But I haven't found it particularly useful in my, poker analysis, although it is something to keep in mind. So I'm not going to talk too much more about that, but you guys are welcome to use Mathematics Poker as a reference and check out all their good stuff about R and various games. So I'm going to fire up the no limit case, and we'll do an EV run again. So it looks fairly similar. So here we go, and again, out of position checks, then in position bets 0.41% of the pot with aces and 29% of his queen-queen combos. That just ends up being alpha of his queen-queen combos, given he's betting R of the pot, or 0.41% of the pot. And then out of position is now calling with all of his ace combos, of course, and then he ends up calling with 42% of his king-king combos. So just to put some numbers on that, apparently the apex of the graph that puts the most money in with king-king is just 0.41 times 0.42 of king-king. It's just going to maximize that value. And since we already were betting half pot in the limit case, which is very close to 0.41% pot, you can't actually see a big difference here from the EV, but realistically, the EV for small blind will be maximized in this case. It'll be like 0.53 whatever, whereas the half pot case was very slightly less. But this is just an interesting way of you can achieve an analytical result that tells you how much to bet, given exactly what each player's strategic options are with their distribution, and that's really what they use this game for. In Mathematics Poker, is they say, well, yeah, no limit. You might think that you just have to guess how much to bet, but you don't have to. You can solve for a bet size, at least in some situations, which I think is a pretty interesting result. So continuing back to the PowerPoint, we'll move on. And then this is the last case that I want to consider. We can finally suppose that in position had to bet a very large size, a size that's greater than the size of the pot. And that's sort of the sort of situation that I think Nick in his post is thinking about a little bit, although obviously Nick is thinking about it in the context of a real poker game where things aren't as cut and dried as in these ace-king-queen games. But let's just think about what would happen if we had to bet pot or check as in position. So the first thing, the first observation is okay, so how often do we bet queen-queen? We already know that we're betting all of our aces because we still have the nuts when we have aces. Let's think, can we ever bet queen-queen? And the answer is no. Queen-queen will definitely be negative EV because out of position is, given that we have queen-queen, is going to have aces half the time and kings half the time. But out of position can never fold aces because it's the nuts. So there's no possible way that out of position can fold 1 minus alpha percent so that bluffing with queen-queen has 0 or positive EV. So, supposing that we bet full pot, that means that out of position should fold half the time. And he has aces half the time and kings half the time, so we'll just call with aces and fold all of his kings. And keep in mind that now that we're betting pot again, we don't create any value in the game tree for ourselves as in position, because we won't actually get any value when we do in fact have aces, because out of position will fold all of his kings. So we've just put ourselves in a bad spot. We've bet too much. So once we bet, our game value again was maximized at 0.414, betting 0.414 of the pot. And our game value continues to decrease as we bet more and more. So for example, say we bet 0.98 pot, out of position would call, with a tiny percentage of his king-king hands, but the frequency times the size that he calls would make the volume of the money he puts in with king-king quite a bit lower than if we had bet less. And then finally, once we reach full pot, out of position folds with 100% of his king-king combos, and we fail to generate any value in the game tree for ourselves. So the game value for in position goes back to 0.5, or just half the pot, since he'll never bluff. Actually, a funny case is if we bet exactly pot. So in that case, we can bet half of our queen-queen combos. So we can maximize our bluffing frequency, but we won't create any value for ourselves. So This goes back to another sort of mathematics of poker point, which is that we bluff in order to get action on our value hands. We don't bet our value hand so that we can bluff. That's getting things completely backward. So if anyone wants to play with this, when I post the card run review files, you can satisfy yourself at this point by realizing that if we bet full pot, we can bet 50% of our queen-queen combos, but it doesn't make us any money. So our queen-queen makes $0 when it bets, and our aces make the full pot as well, because we'll never get called by worse. And then once we bet over the size of the pot, we can never bluff, because we'll only get called by aces, and we'll also never get called by worse. So we just bet aces and win the pot, and we can never bluff, and the expectation of the game goes back to 0.5 for us. And so Nick's question, and certainly I don't think Nick was asking that in the context of this game. I don't want to say that he is, and I don't think he is at all. I'm sure that Nick's very familiar with this game, and I'm not sure. Maybe there are situations in real poker where we can increase the value of our range by making some negative EV bluffs, although I don't think so. I think someone's making a mistake somewhere. But I don't want to completely, tie myself to that statement because there's a lot of situations in poker. But my guess is that if you looked back in the game tree at some earlier point, there would be some sort of situation that that you could have taken to increase your EV in a different way. So can imposition do better by making negative EV bluffs? The answer, as I already said, is of course not. There are no negative EV bluffs in optimal poker. All bluffs are neutral or positive EV. And what this game shows is that there are ways to bet the wrong amount so that we can't bluff. But the answer when we find a situation where we can't bluff is to bet a different size, not to make a negative EV bluff so that we can get paid off by betting the wrong size. That gets things completely backward. And next time, we're going to look at some positive EV bluffs in a different toy game. And just before we go, I will bring back the 1.5x pot bet just to show you guys this result. And here we go. This is the exact same structure of the game tree as you guys have seen before. Betting aces at this point has an expectation of 1 because we're only getting called by aces, and given that we have aces, the other guy never has aces, as we showed. And this is betting 1.1x the pot. And betting queen-queen ever is going to have a negative expectation because out of position can just call us enough by only calling with aces. And the expectation of the game is going to be 0.5 here for in position. And that just shows that you cannot make negative EV bluffs to get action on your good hands, at least in a situation like this. And supposing that the card removal effects are so strong that betting any amount makes a bluff negative EV, that typically just means that we can't bet without the nuts. And usually just that means that the action goes that the player bets with the nuts and the other guy just always folds. And that just means that there's no value in the betting for either player, supposing each player plays well. It doesn't mean that we should start making negative EV bluffs in order to get value on our nutty hands, because the other guy's already going to have enough hands to call us in the first place. So this has been Sauce123 for RunOnce.com. I hope that was relatively clear and fast-paced enough for you guys. And I hope you guys learned something. And I will see you next time, and good luck at the tables.